Okay, so good morning and welcome back. We were discussing, we're discussing one particular configuration of biasing a MOSFET by taking current out of the source, and we came to the conclusion that this particular architecture auto biases itself, and then we delved further into it, and we saw that if we add a voltage source here, an incremental voltage source as the gate, then we could, and we observed the output at the source, then we saw that this V0 was, incremental V0 was almost equal to Vi. And this made sense because even from the total picture, or even if without going into the small signal picture, this is not approximately, this is exactly, because since we are biasing this structure with a constant current source, whatever we do, the current will not change. If the current doesn't change, current through the MOSFET doesn't change, then if I increase the gate voltage by Vi, the source voltage also has to increase by Vi, right? So otherwise, if this condition is not satisfied, then the current will change. And since I am biasing it through a constant current source, this will not change, which means that V0 has to be equal to Vi. That's fine, that is expected. But then we went ahead and said that, hey, I mean, if we do this, let's say I have a resistance RL and I want to connect it to this node V0. Okay, so I want to use this structure. I want to use this structure to drive this this voltage, this resistance RL, and then we did something. Now, before we did the analysis in the previous lecture. You can go back and look into it. But let me ask you one question. This is again going a step back. Let's say I have in the context of this discussion, let's say I have a box. In the box, I have several elements. I have a resistance, I have capacitance, inductance, voltage sources, current sources, voltage control voltage sources, current control voltage sources, all LTI systems, right? We have something like this. And if I connect a load resistance RL across its terminals, let's say A and B, I would expect some current to be drawn, right? So now, without doing, when I expect some current to be drawn, I would expect some voltage to be formed, V out. So looking into this box, looking inside this box, to a layman, it will definitely seem like there is a source inside. Since there is a source inside, I am extracting power out of it. I am getting some voltage at RL. So all we know is whenever we say it's a source inside, it either is a voltage source inside or a current source inside or a mix of both. Okay. So under the condition that I have shown right now, how would you conclude that approximately what does this source look like? Does it approximate a voltage source or does it approximate a current source? Depends on, not only depends on RL, yes, it depends on RL. What else? So what will you? What is the test that you will try to do and see whether this is a voltage source or a current source inside the box? Right. So essentially, exactly the equivalent circuit resistance, because ultimately this is an LTI system. I should be able to model it as a Thevenin's or a Norton's equivalent, which means that if I Thevenize it, I will end up with something like this. Some Thevenin voltage and some open circuit resistance impedance, in this case, let's say ZOC. and this is connected to RL. Or in terms of Nortons, this will be ISC, ZOC, terminals come out, RL will be BA, PB, PA, PB. Now, when I am looking in here, essentially what I am doing is I am looking in here, or I am looking in here, and trying to figure out what the source looks like. So now, if this voltage, if this contraption looking in here is supposed to act as a voltage source, which means the voltage across RL should not change after application of RL also, right? An ideal voltage source doesn't change its value even if I attach any load to it. So there is no loading effect in case of an ideal voltage source, right? So under what condition this will look like ideal voltage source then? RL should be much greater than or less than? Greater than, right? Same condition appears here. Same condition appears here. If you ensure that RL is much greater than this, then it behaves like almost like an ideal voltage source. Or from a designer's point of view, if you are trying to design the box, if you are trying to design this box, you have to ensure the other way around. That is, you are in charge of designing open circuit impedance. You have to ensure that this is less than RL. In this second case, less than or greater than? One second. So are these two cases identical? They're identical, right? So the condition shouldn't change. So in the Thevenized equivalent, what we are trying to ensure is that all of VTH appears across RL, or in other words, there is no significant drop across the Thevenin impedance. In case of the Norton's equivalent, all we are trying to ensure is that there is no current division that happens at this node. All the current load flows into ZOC. So I mean, it basically pointing to the same thing from two different perspectives. Okay, so the moot point is that ultimately, given a network, if I ask you, or if anybody asks you, hey, whether this network is a good enough voltage source or current source, you have to do one experiment. You have to figure out what is the output impedance. If you know that the output impedance of the network is much lesser than the load that you are trying to drive, then it's a what? Then it's a voltage source. And if it's the other way around, right? If it's the other way around, right? For example, if this is not satisfied, let's say I'm not saying not only satisfied, it's completely the other way around. Let's assume if ZOC is much greater than RL, then what comment can you make? Then it becomes a current source, because ideal case, if ZOC is infinite, look into the Norton's equivalent. If ZOC is infinite, this goes off, all the current goes into the load. That's the property of an ideal current source, right? In other words, if ZOC is infinite, the current going into the load, IRL, is ISC. In general, IRL equal to ISC times ZOC by. Now, if ZOC goes to infinity, right? If ZOC goes to infinity, this becomes approximately equal to ISC, right? So if you want to make a box look like a very good current source, then again everything is relative to the impedance that you are trying to drive, right? So if you know the impedance that you are trying to drive and you want to make a box look like a very good current source, all you have to ensure is that the output impedance of that box should be much higher than the stuff that you are trying to drive, right? So in a nutshell, when you are trying to make a voltage source, right, the good property of a voltage source is its output impedance should be zero. Zero you cannot make. All you have to do is to make it sufficiently small enough. Now, what is sufficiently small enough? It's all relative. Small enough with respect to what? Small enough with respect to the load that you are trying to drive. If you are trying to make it a good current source, you have to make the output impedance very large, infinity. Again, infinity is a relative term. You cannot really go to infinity. You have to make it large enough. What is large enough? Large with respect to the load that you are trying to drive. Okay, make sense? Does that make sense?
Then what is the condition that RL should be greater than ZOC? What is this condition for?
You tell me now. Or ZOC much less than RL? What will that give us?
The total current will go to ZOC.
Fine. And yes, total current will go through ZOC. Fine. So it's not a current source then, right? Not a good current source. Then is it a good voltage source? Why?
Because the current will go. RL is higher. So the current VTH will be.
Yeah, I mean somebody else? Yeah, exactly, right? So the output voltage will not change, right? If ZOC is much less than RL, the output voltage will not change even if I change RL, right? So that's again a good voltage source. If you buy a AA battery from eShop and you plug in something and you see that output voltage changes, then obviously it's not a good voltage source, right? You'll have to go and change the battery, right? So what does a good voltage source mean in essentially? I mean, bad voltage source will entail that it has a high output, it has a relatively high output impedance, right? So it's getting loaded. Moment you are trying to draw charge out of it, there is a drop across its terminals. That's what it means, right? What is a drop across its terminal? What do I mean by a drop across its terminal? It means that its output impedance is not zero, right? Nothing will be zero. It will be some finite, but that finite has to be much lesser than what you want. What you want is ultimately the battery voltage to appear, right? So that's what is what you don't want any loss. The loss is equivalent to the drop. Okay, so now we can express the same thing in terms of a Thevenin's equivalent or Norton's equivalent. It doesn't really matter. We are essentially saying the same thing. But you need to understand that given a circuit, what is the condition we need to satisfy in order to make it look like a voltage source. Okay, so now if we are okay with this, let's revisit this network. And I want to use this circuit to drive a voltage, so drive a resistor RL. Now, I didn't spend too much time on it, and in the last class I had simply connected a capacitor here. But even before going to the capacitor, can you tell me what will happen if I directly connect these two nodes? Right. Yeah, so there will be some, I mean, we bias this transistor, assuming that I would want this I0 current to flow through the transistor also only. Now, if I connect these two nodes directly, then obviously that's not going to happen because some part of the current will be going into, DC current will go into RL. So that will obviously change my quiescent point. Now, whether the change in quiescent point is significant or not, that depends on analysis. But to start off, I do not want any deviation in quiescent point. Right. So if I do not want any deviation in quiescent point, the best thing that I can do is match this voltage to whatever Vs I had. Right. If I match this voltage to whatever VSQ I had, then it should not be a problem. But I cannot do that here because the quiescent voltage across RL left as is zero. So the alternate is put a battery of value VSQ and then connect these two. Right. So then I will not be drawing any current into this network. If I don't draw any current into this network, then all the current I0 flows through the transistor. No harm done as far as the quiescent point is concerned. But now before BitSem and also in last few lectures, we saw that this is something that is not feasible, but a poor man's battery is a very large capacitor. Right, so a very large capacitor, I can replace the battery with a very large capacitor, And given enough time, this capacitor will get charged to quiescent voltage of VSQ. Right? Under quiescent condition, this will get charged to VSQ, and there will be no current that will be drawn through the capacitor. Okay. So now if this is C infinity, right? If this is C infinity, so I can then try to figure out what will be the voltage. I mean, what will be the voltage at V0? What will be the incremental voltage at V0? Now, we did this analysis in the last class. I would like to draw your attention to one particular thing. That is, now in the incremental sense, this is what my network looks like. V0. Let me sketch this RL with a different color because this is the load. Now, if I ask you that without doing too much analysis, can you tell me whether this circuit while driving RL behaves like a voltage source or current source? What will you do? From the discussion we had like last 5 minutes, what will you try to find out? Yeah, so you would like to find out the output impedance, right? So what is the network? In this network, the network is this. And you would like to find out the output impedance. That is, you are trying to find out what is the impedance looking in. Right? So how do you find out output impedance? What is the first thing that you do? You short all the independent sources. In this case, the independent sources is Vi, so you short it. You apply a test voltage and find out this current I test in terms of V test, right? So in this case, this voltage is 0. This current is GM0 minus V test. So the current I test going upwards is GM times V test, which means that your ROC is 1 over GM. Okay. So now if we have to, which essentially means that I have got the output impedance of this network, this 1 over GM. Looking into the source of your MOSFET, you get an impedance of 1 over GM. Now, if I ask you whether this is a, yes. Right.
Because if we increase the so VGS is very high.
Okay, so okay, make your point. Go ahead.
Suppose VG is very high.
Okay, suppose VG is very high. Okay.
VG is very high.
Right. Right.
And we ideally want that charge.
Right.
Battery also
Right, it will, right? But then when you have a battery, if you, okay, let me repeat his question. Maybe I might have misunderstood it also. So what you are essentially saying is this, right? Let's say this is VG, what did I write it here? I didn't write it. So let's say VGQ, okay? And this is my setup, right? So you said that I turned it on suddenly, right? So let's assume that this VDD is there, this battery is there, some VSQ. Let me put numbers. So let's say this is 3 volt. This is 1 milliamp. And if things work properly, this is supposed to be 3 volt and this is supposed to be 1 volt. So let's assume that this VSQ is 1 volt. That's how, let's say I have sized my transistor. So now what you are saying is, let's assume that this was 0 and I suddenly turned it on, right? Right. So yeah, so essentially what you are saying is, if this is a step input from 0 to 3 volt, right? What's going to happen? This is what you're saying, right? So when it's 0, your transistor is off.
So when we are applying the control VG and PS is this.
Right.
So large amount of
Yeah. So when you are increasing the voltage, a large amount of current will flow. I agree, right? So the easier way to think about is this, right? You put a capacitor here where everything is 0, where this voltage was initially 0, and you increment the gate. So then the amount of current that will flow will be more than 1 milliamp or less than 1 milliamp. It will be more than 1 milliamp because this was 0, this is 3 volt, right? So which means that if we take a number, let's say this mu n Cox W over L was 1 milliamp per volt squared. It is that 2 milliamp per volt squared. So and if this is the case and you turn it on, so what is the amount of current that we are going to draw? VTH is 8 milliamp, right? So you are suddenly drawing 8 milliamp, and this is okay, 4 milliamps. So you are drawing you are pushing 4 milliamp into the node, 1 milliamp is sucked out. Where is the 3 milliamp going? Right, it should go to the battery. So it will go into the battery. In case of a capacitor, it will go into the capacitor and charge up the plate. And how long will it keep charging? Right. So this plate of this capacitor plate will rise. It will go from 0 to some steady state value, and steady state value will be 1 volt. Right. So as this source voltage rises, this current will decrease. This current will decrease from being 4 milliamp to 1 milliamp. That's what's going to happen. Was that your question? Okay, now let's put a battery. So now let's put a battery. So now the things will become tricky if you put a battery, because now when you are putting a battery, when this is at 0, right? When your gate voltage is 0, you don't have any current. No, it starts from 0. It starts from 0. There is no current through the MOSFET. Now you yanked it up to 3 volts, right? So when you yank it up to 3 volts, this current is supposed to be how much then? No. It will become 1 milliamp and it will settle automatically. So another way to look at it is that a battery, you don't have any time constant issue with a battery. There is no charging time, discharge time. Exactly, right? You have to, if you have to put a battery, you have to identify it beforehand, and not only identify it beforehand, you have to be accurate to the nth decimal place, right? Because I took numbers which are very friendly, right? 1 volt of threshold voltage and 0.2 and blah blah blah. All those numbers will change as different temperature changes. If you measure it today, if you measure it tomorrow, with wear and tear, all these numbers change. So which means you have to every day keep on changing the value of the battery yourself. But if you put a capacitor, you don't have to do that. It will automatically get charged to whatever it needs to. Okay, good. So now going back to the thought. So if I have to use this stuff as a voltage source, I know what is my output impedance. What condition do I need to satisfy now? I want to drive this. Yeah, so I want to use this circuit to drive RL. I want to use this network to drive RL. The condition that I need is 1 over GM, that is output impedance, to be much smaller than RD, right? So I need 1 over ROC to be much smaller than RL. This is for voltage source constraint, right? For a good voltage source, which means that 1 over GM has to be much lesser than RL, or in other words, the condition that we came up with yesterday is this. Okay, make sense? Okay, fine. So before we move on from this particular configuration, there is one last point that I would like to make is in the incremental sense. If you recall the way we came up with the same network in two ways. One was while we are trying to bias our network by adding a constant current source at the source, and also while we are trying to get a voltage buffer kind of thing, right? Where we are trying to get an output which tracks the input. So while we were trying to get an output which tracks the input, I made a comment that you'll have to first get an error voltage V0 minus Vi or Vi minus V0 and drive this error to 0. Right? I wanted to drive this error to 0. If I can drive this error to 0, then automatically I will ensure that V0 tends to Vi. Right? So that was a thought process. And we did this using first principles. And this is what we ended up with. So why does this now? I mean, now that after this, we did some mathematical analysis, but we didn't revisit whether this is indeed in negative feedback or not. So let me spend a couple of minutes to delve into this. So now let's assume that, let me take a cue from the question that he asked. So let's assume that this Vi increased, right? This Vi suddenly increased. And let's put a small capacitor CP to impose some semblance of time, right? If there is no capacitor, everything is instantaneous. So if let's assume this Vi increases, if Vi increases, this current source is trying to push in more current. Since it is trying to push in more current, this V0 will increase, right? Since this V0 is increasing, this very act of increasing V0 is shutting the current source down. It will not fully shut it down, obviously, but it's tending to reduce the current, right? So an increase in the input, so when input increases, this current is tending to increase. The current is tending to increase, the voltage is tending to increase. Since the voltage is increasing, it is trying to reduce the current. And this everything will settle. Everything will settle when there is certain condition that is met, right? If for example, GM is infinite. This is again a hypothetical leap. Assume that GM is infinitely large, right? Let's assume GM is infinity. If you assume GM tends to infinity, what can you comment on, without doing any calculation, can you comment what will be the steady state V0?
It will be equal to Vi.
It will be equal to Vi. Why?
Because GM Vi by 1 plus GM RL.
Okay, you are going back to the calculation. I don't want to go back to the calculation. Can you, without looking into the formulae, can you tell me why V0 will be equal to Vi? Why should it make sense?
I know it's constant, so we can't implement.
There is no I0 here, right?
If they're unequal, then they can infinite. So
yeah. So that's essentially. You had a point. Your transfer parameter is infinite, so
whatever we are going to have input.
Okay, but those two statements are independently correct, but they are related. I mean, in the sense that your output will then, I can argue the output will go to infinity.
The current this is the current, but the V not actually goes, and this V not gets transferred because the transfer current is.
Okay, yeah. So that's actually correct. I mean, it's the same thing that you also pointed out. So if GM tends to infinity and you assume that V naught is not equal to VI, right? Let's assume V naught is not equal to VI, which means this will push an infinite current. It will keep pushing infinite current. Right? If it pushes infinite current, V naught goes to infinity, right? V naught keeps on going and it will go to it will cross VI, isn't it? So that's not a feasible scenario, right? So the only possible scenario is you have the currents VI minus V naught has to go to 0, because in principle you know that if I multiply infinity with 0, at least in the limit, I can get something finite, right? So essentially the only possible scenario in this case is if GM keeps on increasing, right? As a designer, if we have to make a very good buffer, a very good voltage follower in this case, or voltage source, all you have to ensure is that GM tends to infinity. Again, the infinity is a relative concept. You'll not be able to make infinity, but you have to make it higher and higher, as high as possible. In this case, as we saw, it has to be 1 over GM has to be much less than RL, or in other words, GM has to be much greater than 1 over RL. Okay. So basically coming to the same conclusion from multiple different angles. So now a couple of jargons. This particular architecture has multiple names. If you go through the literature, you will see that it's called number 1 is obviously voltage buffer. Number 2 is voltage follower. Number 3 is source follower. And all this should now make sense. I mean, voltage follower, simply because the voltage at the source follows the voltage at the gate. Source follower essentially means the same thing. Voltage buffer, the name voltage buffer comes because you are shielding if the input has a source resistance, I mean input has a resistance, let's say RS, you are not connecting the source directly to the load, right? So if you have a load here, you are not connecting the input voltage source to the load, you are shielding it, you are buffering it, and then connecting an attachment to it, right? So you are buffering the voltage and sending it out to be driven to the load. So that's why it's called a voltage buffer. There is another name to it. This is called common drain architecture. It's called common drain because you can appreciate from the incremental sense, the drain is shorted, right? So you can assume the drain to be grounded, and you are applying the input between gate and ground, and you are observing between source and ground, right? So it's called a common drain architecture. Just like we had a common source architecture where the source was grounded and we were observing it. I mean, we were applying between gate and source and observing between drain and source. Here you can argue that we are applying the input between gate and a short, where short is a drain because drain is also shorted, and output we are observing between source and a short, or source and a drain which is shorted. So it's called a common drain architecture. Yes. You mean why GM tending to infinity? Okay, so let's assume that GM tends to infinity and V naught is not equal to VI, right? So if V naught is less than VI, right, then if GM tends to infinity, then you are trying to push in infinite current. So when you are pushing in infinite current, or rather when you are pushing in very large current, what are you trying to do? You are trying to increase V naught, right? So when will this tug of war end? In the sense that when you are increasing V naught, you are reducing Vi minus V naught. So when you are reducing Vi minus V naught, you are reducing the strength of the current source, right? So this will keep on happening. So you are reducing the strength of the current source, and as you are increasing VI, the V naught. So when will this balance? When will you get to that balance? The balance you can only get when VI equal to V naught, right? Right. So there was a midterm question also where I think I may ask that what happens if something goes to infinity. Yes, right. You will see that your output actually settles to some value. But there was one tutorial question also where I asked when y21 goes to infinity, what happens, right? So these are related, and you have done this in a different context. You have done ideal op amps, right, in ESC 201. In ideal op amps, when you set A to be infinity, you have this virtual ground that appears. So what is a virtual ground? It means that one node tracks the other, right? A virtual ground, I mean, if in case of an op amp, and you set A to infinity, what you are essentially saying is that these two nodes are tracking each other. So if I apply some DC voltage here, let's say VDC, this will also go up to VDC. They are tracking each other, right? So this happens only because you have A tends to infinity. If A is not going to infinity, it's not going to track. I assume you have done this in ESC 201.
It was only for the negative feedback.
Yeah. It's a negative feedback, right? So same thing here. If GM tends this, do you agree that this is the negative feedback? This is a negative feedback. GM tends to infinity. Means you are establishing a virtual ground. You are establishing a virtual ground between the gate and the source incrementally. And that is why gate and the source are tracking each other. The difference between the gate and source are going to zero. Right? Make sense? Okay, fine. We'll deal with op amps virtual grounds formally in negative feedback in after midsem, but this is something that you can keep in your back pocket. Okay, fine. So let's move ahead and let's say that I have had enough of this current source. And I want to this is PGQ. I want to replace this current source with a transistor. Okay. So given whatever you know till now, what do you think is a best way of replacing this current source or current sink in this case with a transistor? What can I do? What is again, let me help you out. What is how do I know it's a very good current source?
For low values of low values of R, then the current is safe.
Okay, that's fine. That's true. That's agree. You had there was a comment here. The question is, I mean, again, if I have a box and I am trying to figure out whether the looking in impedance is high, whether it's a current source or not, what am I looking for? Impedance has to be very high, right? Infinity, ideally. But in the absence of too much of information, it has to be high with respect to whatever I have connected, right? So now, given that you know what a transistor looks like, right? So what can I do if I want to replace this current source with a transistor? Not really. Okay, so let's do the diode connection. So he's saying that if I put a diode connection here, right? This is what you're saying, correct? Okay, so let's try to figure out the impedance of this diode connected stuff, right? So now this stuff inside the box I'm looking in is essentially looking here, right? I'm trying to figure out what is the impedance looking down, right? So what do you think is the impedance looking down of a diode connected device? And I think this was again a part of one of the tutorial questions. Not in this sense, but in some other sense. Is it? So let's do the same thing, right? So assume this is in saturation, blah, blah, blah. And how do I figure out what is the impedance? What should I do? Connect a V test, and let me sketch the incremental equivalent of this. The gate was here, drain source, gate and drain are connected. V test. I have to figure out what is I test. What is this current? What is this expression? This is GM times. This is not rounded, right? This is gate VG. So this will be GM times what? What will this current be? GM times V test, right? Because VG minus VS, VG is V test. So VG minus VS, which is V test minus 0, right? So this I test is essentially GM times V test, right? So I test is GM times V test, which means what is your impedance? Or ROC, output impedance, is 1 over GM, right? So is this a good current source? It's far from infinity, right? No, so I wanted to figure out whether I can replace the current source with this diode connected, right? So I'm trying to figure out what is this. So if I replace this with this, then I am going to trying to figure out the stuff that I have replaced with is a good current source or not. So that's why I'm not bothered about the upper part, right? So if I have to bother, so ideally you want things to be infinity, but if you are not getting to infinity, you have to then figure out whether it's much larger than something, right? So in that case, the upper part will come, because when I am saying it's a good current source or not, I am trying to compare its impedance with respect to something that is attached to it, right? So what is attached to it? It's the upper part. What is the impedance of this upper part? Looking up. We just did this. Can you tell me small signal impedance of looking into the source? 1 over GM, right? So if this is, let me call this M1, this is M2. This is 1 over GM1, looking up. Looking down is 1 over GM2. Transistors are made of the same material, so GM1 and GM2 is almost of the similar order. So obviously, this cannot be a very good current source. The stuff in the bottom, the direct connected transistor cannot be a very good current source. Okay, so what else? What else can we do? A transistor has three terminals, out of which 2 are conducting. You have eliminated source, because looking into the source, you get 1 over GM. What else remains? Gate you cannot, because no current goes into the gate. So if you connect gate to drain also, it's not working. So what remains? So you have this transistor. Let's say you have this transistor, right? So in the incremental sense, if I look in through this and we short this, I get 1 over GM impedance. Correct? In the incremental sense. Here, even though I get infinite impedance, it's useless because I cannot draw any current. What happens if I look from here? How much impedance do I see? Is it? Looking from the drain, do I get 1 over GM? What is the incremental model of a transistor? It is right. It would have been 1 by GM if you had connected these two, right? If you have not connected, and let's say this is incrementally shorted, what is the impedance looking into the drain? This is Gm times Vg minus Vs, where gate is shorted, drain is source is shorted, so this is 0. So what is the impedance looking from here? Again, do the same thing, right? Apply a test voltage. How much current will I draw? I'll draw 0 current, right? It's open circuited, right? So it's an infinite output impedance, right? Shouldn't surprise us because a transistor is a voltage controlled current source. It's a current source, right? By definition, it's a current source, isn't it? I mean, if you check the ID/VDS characteristic is flat in saturation, which means the current doesn't change. It's a current source. If you just use a transistor as is without connecting, I mean, provided things are in saturation and you don't connect gate and drain and all those things, it's a current source, right? Okay, fine. So which means that, I mean, let's say I have some battery here and I am replacing this current source with a transistor. And let's say I want 1 milliamp current. I want 1 milliamp current through this. So what could I do to ensure that this M2 sinks in 1 milliamp? Well, how should I size M2? Assuming it's in saturation. What should I do to the gate? Can I keep it floating as is? No, obviously cannot. I have to ensure that it's at least on because it's supposed to sink in 1 milliamps. Should I ground incrementally or absolutely? Incrementally ground it, correct. But if I have to bias it, then I have to apply some voltage, right? How do I figure out what voltage should I apply? Right. So 1 milliamp I can put into that equation and then figure out, right? So if I put this IDS equal to half, assuming things work, right? Assuming things are working. So if I put 1 milliamp, which essentially means that I'm trying to figure out what this VGS will be. So that is VTH plus under root 2 IDS. So you know everything on the right-hand side. You know VTH. I told you that I need to sink in 1 milliamp. So you will figure out some voltage. Some voltage will appear, right? So let's assume some voltage appeared and you applied a battery of that voltage, right? So given all the specs we have been using repeatedly through this class, let's assume that this is 2 volt, mu n Cox W over L is 2 milliamp per volt square. So you figure this out. This is what this is supposed to be. This is fine. So now, since this is not a actual current source, this is a current source that we have made up. Yes. Yeah, that's the question. So that's the question. How can, since this is not an actual ideal current source, we have made it up. So you have to ensure that this is in saturation, right? So how can we ensure that this is in saturation?
So why are we trying to remove the current source and replace it with another
Yeah. So essentially, you can make current source with transistors, right? So we'll not get into making actual current sources with transistors, just like we'll not get into making actual voltage sources using transistors. So let me ask his question, answer his question. His question is, why are we interested in replacing a current source, right? So as it turns out, when you will be designing, you will be given one current source, you will be given one voltage source. Just like if you given one voltage source, you'll be given one current source. Just like you don't use one battery for each transistor that you are making, you will not be using one current source for each transistor that you are trying to bias. So you will have a master current source. So you have to derive everything from that master current source, right? So we'll get to how we will derive from master current source, but for the time being, let's assume that there is a master current source, but we'll get to how to do that. But if we have to use, given that we cannot use one dedicated current source per transistor, what else can we do? I have another transistor, right? So now putting up, yes.
So we can connect a very high resistance between the gate and the drain.
We can connect a very high resistance between the gate and the, yeah, that's a very good observation. But before going there, let me answer his question that how do we ensure that M2 remains in saturation all the time without doing what you said right now? So what do you think is going to happen? Let me call this battery VGQ1, and this is the bottom one is 2 volt. Okay. So who do you, I mean, if things are operating properly, what do you think is setting the current in this stack? Which transistor is setting the current in this stack? M2 is setting the current in this stack. When I say that, who is setting the current in this stack? What I mean essentially is that if I change this gate voltage of M2, the current changes, right? If I change the gate voltage of M1, will the current change? It will not change, right? Because we did this, right? We did this with a fair amount of detail. What will happen if this voltage increases? This voltage will follow, right? So the current in this stack is being set by M2. So given that we know that, now you tell me what will happen if VGQ decreases.
Yes, sir.
This will decrease. How far can it decrease? If it decreases, is anything bad going to happen? Which one? M2 might go into lean, right? So how do you ensure that M2 is always in saturation? In this particular configuration, which is your knob that you have to tweak to ensure that M2 is in saturation? No. I don't want to connect anything to anywhere. This is what it is. Yeah, I can change VG. VGS2. No, so I want 1 milliamp, which means I don't want to change this. I don't want to change the sizing of M2. This is whatever we have. VGQ1 is the only handle that I have, right? So as long as I ensure that VGQ1 is higher than something, right? My transistor M2 will always be in saturation. Correct? What is that something? That is easy to figure, because if I know this is 2 volt, what is the minimum voltage that I require at VS? 1 volt, right? Assuming threshold voltage of 1. If this is 1 volt and I want 1 milliamp current to flow through M1, right? And let's again assume that mu n C ox W over L is the same 2 milliamp per volt square for M1 also. It need not be, but let's assume that, which means how much VGS I need for M1? How much VGS that I need for M1?
3 volts.
2 volts. Right? Right? Which means this has to be 3 volts at least. Right? Anything lower than 3 volt, you're in trouble. Okay? Okay, great. Thank you. We'll meet after the break.